for posterity. So I hope everybody's okay with that. Welcome to today's edition of the Bridges-2 webinar series. This is hosted by the Pittsburgh Supercomputing Center. And here's a brief background on us. And I give you a couple of seconds to read it, but maybe you're familiar with us. I do think that you're familiar with Bridges-2 because I think y'all are using it. And welcome on behalf of the Bridges-2 leadership team. My name is Sergio Sanielewicz. I'm the principal investigator. And again, welcome on behalf of our leadership team here and of course of our entire PSC crew. So our Bridges-2 webinars are a forum for the community to learn and share ideas and achievements. And here's the link, and I think Tom also put it in chat. So here you can see this is the third webinar in the series. You will be able to see the recording of this one and the slides. And you can also look at the two previous ones, which were given in this series. And there will be, we have two more scheduled, one actually later in June, and then there's going to be one maybe in August. So the idea is to have topics, to find topics and speakers of interest to work that's being done or may be done in future. Our theme so far mostly has been on efficient use of multiple GPUs in jobs, but not only. Yeah, if you have ideas for future speakers, including yourselves, please just send email to me. And so we have the pleasure today of hearing a talk by Dr. Mitchell Dorrell, who acquired his bachelor's in physics from Rowan University, PhD in physics from University of Delaware, came to PSC in July 2021 from the NIH. And maybe if you are doing GROMACS actually, then you probably have interacted with him because he supports it. And that's what he's been going to be talking about today. But among other things, Mitch also leads the Bridges-2 software installation task force. And so as part of that, he's looking at ground up at the entire software stack and how we can best install, support it, both, the applications that are supported by PSC staff, but also ideas for you guys if you bring your own software. So he's a good person to know. And before I turn it over to Mitch, the logistics today, all of us will be muted except for the speaker during the presentation. So we will save the last 10 minutes for Q&A. Please, as questions may occur to you, just type them into the Zoom chat. And I know I'll be watching. I think Tom will be watching. And we may be able to address some of them just as, Mitch is presenting, maybe some more general questions, things like that. But then at basically 50 past, when Mitch finishes his presentation, we will go over the questions that have been asked. And so he'll answer live. And then, there may be some additional questions or unanswered questions. So then you can interact with him using his email address. So are there any questions before I turn things over to Mitch? Not, then Mitch, it's all yours.
All right, let me start the slideshow. And let me share the screen. How does that look?
It looks good.
Perfect. And okay, so to start here, the first thing I wanted to tell everybody is that I am having a bit of an audio issue lately. I have a damaged cable that I have to use. A consequence of that is that occasionally my signal cuts out. If that happens, hopefully one of my colleagues will let me know so I can fix it. It's not a big deal, but I just wanted to let everybody know that that could happen. Hopefully it won't. It doesn't happen that often, but it might. So I wanted to warn you about that. And then I wanted to just give a very, very vague overview of the structure of my presentation. So I'm going to be honest, we're going to start off with some heavy stuff right off the beginning, even a little bit of physics, not a lot, but just a little bit. That's important for the context later on. Then we'll get into some lighter stuff involving the logistics of how Bridges-2 works, and a lot of that will also be in the user guide. And then finally, we'll get into some of the more complex stuff about how to specifically balance your jobs on these Bridges-2 nodes and really get the most out of your service units. The other thing I wanted to warn you all about is that none of these slides is complete. There is more to know about literally everything I cover. So nothing I say today is an unqualified universal truth. Everything here is being simplified. And I include a few links to the documentation throughout my presentation. If any of you decide to investigate those links, you will see what I'm talking about. I might discuss 3 or 4 options out of 100. So, and with that also being said, is I will try to remember as I go through, actually, you know what? It doesn't look like it's going to be easy for me to do so. I was hoping to, oh wait, maybe I can. Yes, okay, I will be able to. I'm going to try to copy the links to the documentation as I talk about them into the chat, so that way you don't have to try to hunt them down in the in my slides afterward. So you can save the ones that you think are you're most likely to refer to. Okay, with that said, let's get into it. So I'm going to start with some basics of molecular dynamics and preparing simulations here. In the most general sense, molecular dynamics is evaluating Newton's laws of motion for a box full of atoms. You're putting a lot of atoms in a box and you're watching what happens. In addition, we typically use periodic boundary conditions, which means that there are no walls. So as soon as we define a simulation cell, and as soon as atoms walk off one side of the simulation cell, they will immediately re-enter from the other side. This means that our computational model is, this means that our computational model is effectively infinite. The next thing to say is that atomic interactions are defined by the force field. So when you are setting up your simulations, you choose a force field. This force field covers all of the different parameters that define how one atom interacts with the next atom. There are generally 3 categories. There are the bonded interactions, which are spring-like or Hookean potentials, for those with a physics background. These represent all of the interactions between atoms within the same molecules. So if you have something like H2O, then you would have basically 2 bonded interactions there, actually sort of 3. You'll have oxygen with the first hydrogen and oxygen with the second hydrogen, and then you'll also have an extra interaction to basically apply a spring force to the angle between the 2 hydrogens around the water, around the oxygen. So those are your bonded interactions. The next category are your Lennard-Jones non-bonded interactions. If any of you are familiar with the 612 potential, this is essentially an approximation for how atoms attract and repel each other over distances between molecules that are not bonded together. And then finally, we have Coulombic interactions, which is a fancy way of saying electrostatics, or positive and negative charges attract, but any 2 atoms with the same sign will repel. The next thing that you have to think about with molecular dynamic simulations is the thermodynamic ensemble. So when you're setting up a simulation, you have to choose what your constants are going to be. Most simulations, almost all simulations, involve setting a constant number of atoms. Those will be that's your N. But then many of them will also set a constant volume. So that would be NVE or NVT, or constant pressure, which would be NPT. And then finally, you typically either configure your simulation to retain a constant total energy or a constant total temperature, which is what the T's stand for. So those are your general three types of thermodynamic ensembles. Since most realistic situations are not in a pressure vessel, the pressure is generally considered a constant. And since most of them are not in some thermally isolated system, the temperature is usually a constant as well. NPT is generally the most common thermodynamic ensemble that's used for a lot of simulations, especially biologically relevant ones. But there's a catch. Coulombic interactions get complicated. So the problem here is that when you think about a simulation with an infinite number of atoms in it, because even though our simulation box is finite, the number of atoms in our model is effectively infinite. You can think about how many atoms are positioned a certain distance away from some atom that you pick. So what will happen here is if you pick an atom, like maybe it's just some random carbon atom, and you look at all of the other atoms that are maybe 10 nanometers away from it, you can count in the number there, we'll call that N. But then if you look at all the atoms that are 30 nanometers away from it, you'll notice that there's 9 times as many. So the number of atoms in each shell as you go farther and farther away increases proportional to the square of the distance. If we have infinite atoms in our model, though, which ones do we use when we evaluate Newton's laws of motion? So the answer to that depends on the different types of interactions. For the bonded interactions, each atom only has a few bonded interactions with its neighbors inside the same molecule, so we will always use every bonded interaction. For non-bonded interactions, we can choose a cutoff because the Lennard-Jones potential decays at a rate inversely proportional to the 6th power of the distance. That means that as your shells get bigger and bigger and bigger, you get more and more atoms, but the potential gets weaker faster than the number of atoms grows. That means that the total influence on your atom from atoms at a distance goes to 0. Unfortunately, for Coulombic interactions, that doesn't work. Coulombic interactions diminish inversely proportional to the distance. So instead of being the distance to the 6th or to the distance squared, it's just 1 over the distance. That's a problem because there are more atoms in the outer shells than the potential weakens. In some sense, let's say you have, I'll just choose some random numbers. Let's say you have 10 atoms 10 angstroms away. You would have 90 atoms 30 angstroms away. But at 30 angstroms away, your potentials are only a third weaker than they were in the near distance. So the total influence of the outer shells gets stronger and stronger and stronger as you go farther away, which becomes a problem because at this point, any cutoff you choose, you are excluding the interactions of a significant number of atoms. You can't say, okay, I only care about atoms within a certain range. That is not an acceptable approximation in most cases. This is resolved using a technique called particle mesh Ewald. And in short, this uses totally different types of computation on a totally different type of data. Well, same type of data, but a different data set. Whereas the Lennard-Jones and bonded interactions will only act on the atoms that are very close. The particle mesh Ewald calculations need to know all of the information about all of the atoms. It needs to know where every atom is in order to perform those calculations because every atom matters. It computes them in Fourier space, and in general, it's a very different calculation kernel, if we want to call it that. I'm walking through this because the fact that the Coulombic interactions are different will become very important later when we need to balance our interactions on the different types of nodes. So the next thing I want to talk about here in terms of the background is getting access to Bridges-2. So the first step in running any sort of simulation in any sort of research project is coming up with an idea. And to be honest, that's probably not something I can help you with. Different people have different approaches to it. Some people come up with their best ideas when they're out taking a walk through the city. Other people get their best ideas in the shower. It's going to be different for different people, and there's no one way to get an idea. But once you have an idea, I can tell you what to do with it. So most of our researchers get access to Bridges-2 through a system called Access. Access is, I've pasted the link here. I'll copy it into the chat for you. Access is the successor to Exceed. If anyone has experience with Exceed in the past, it's essentially a way for researchers across the country to be able to get access, for lack of a better way of saying it, to computational resources at a service provider institution located somewhere in the country. Pittsburgh Supercomputing Center is one such service provider. And so if you go to accessci.org and you submit a proposal, then your proposal will be reviewed. And if selected, you would get credits that you can then spend on your supercomputing resources. Regarding credits, when you're applying for an allocation, there are 4 different allocation levels that you can consider. The first one is the Explore, which is good for any sort of proposal that's going to need 400,000 credits or less. The next one is Discover, which is for up to 15 or 1.5 million credits. The next one is Accelerate, which is up to 3 million credits. And then after that, there's a Maximize tier where it's very carefully considered on a case-by-case basis, and it's generally for even larger requests than the ones I've listed here. So the reason why you have these different levels is because as you move up the list, you have to submit more and more documentation, and your proposal has to be more detailed and more well justified in order to get the larger requests. But the smaller requests for Explore is very, very accessible. And I want to encourage people to definitely check out, if they ever have an idea they want to investigate, check out the Explore requirements. You'd be surprised at how accessible we make it. Now, these are measured in credits, and credits are not what you spend at the Bridges-2. What you have to do is you have to convert the credits into service units. Service units are the specific currency, so to speak, that each resource provider manages. So, for example, different resources will be worth different amounts of service units. In particular, during this discussion, or during this webinar, I'm going to be talking about GPU and CPU nodes and GPU and CPU resources. At Pittsburgh Supercomputing Center, 13 GPU credits cost the same amount as 700 CPU credits, which means that the GPU credits, sorry, I misspoke. 13 GPU service units cost the same amount of credits as 700 CPU service units, which means that GPUs cost about 54 times more than a CPU job. And that's because there's just simply aren't as many GPU nodes to go around, and GPU nodes are generally more expensive. So the next thing I want to discuss here is starting to talk about, once you get onto Bridges, once you've got your allocation approved and you've chosen to convert your credits to service units at Bridges-2, there are a few different partitions on Bridges-2 to discuss. There are regular memory partitions, which is the default CPU-only resource. We have the regular memory 512, which are the same nodes but with extra memory. These take the same type of service units, so they're not distinguished from the access perspective. You just apply for regular memory and you'll get access to both of them. We also have extreme memory partition, which is a different category through access. And we have our GPU nodes. Each GPU node has 8 NVIDIA V100 GPUs inside of it. We also have RM shared, which covers pretty much the same pool of nodes as RM, the exact same hardware you'll get access to. But the difference is for all of these partitions, when you run a job on those partitions, you have to allocate a whole number of nodes. So even if you only need half a node to run a job on any of these partitions, you would have to allocate the full thing. In order to make things more efficient, if you only need half a node, you can use RM shared in order to allocate a fraction. And you can allocate significantly less than a half a node as well. RM nodes have 128 cores, and if I remember correctly, you can allocate as little as 1 core on those nodes, which is a great way to save your service units. We also have the GPU shared partition, which does an analogous thing, but for GPU nodes. The specific thing to know here is that the GPU shared partition, instead of being allocated by CPU core, it's allocated by GPU. Since each node has 8 GPUs in it, you have to allocate at least 1/8 of a GPU shared node. I'm going to add another link into the chat here because the Bridges-2 user guide has a lot more information about all of these partitions. So I encourage you to refer to that for more detail on all these different types of nodes. But for GROMACS specifically, GROMACS is not a memory-intensive application, which means that the RM512 and extreme memory nodes are not relevant for us. For our researchers running GROMACS and most molecular dynamic simulations, they're going to want to choose RM or GPU service units. I didn't say this, but also the RM and RM shared, they use the same service units, and the GPU and GPU shared also use the same service units. So once you have made your decision about what type of credits you're going to convert or what type of service units you're going to convert your credits to, it's time to connect to Bridges-2. I'm going to move through this type of section pretty quickly because it's really outside of the scope of this discussion. But essentially, most users connect to Bridges-2 using an SSH client. On Windows, 2 SSH clients that I'm aware of are PuTTY and MOBA Xterm. These are not recommendations of mine. I don't know that much about these tools. They are just simply examples that I know that a lot of people use. For Mac and Linux, the SSH command is installed by default. You just have to open up a terminal and type SSH, and it's already there waiting for you. Once you connect to Bridges-2, you will be connected into a login node. We have a small pool of login nodes, so each time you connect, you might get to a different one, but they all share the same file system. So the login nodes are primarily used to dispatch jobs to the compute nodes. You cannot connect directly to the compute nodes from home. You have to access them specifically through the login nodes. But once you are in a login node and you start a job, whether it's a scheduled job or an interactive job, you then have the ability to connect into the compute nodes. There's one more type of node that I want to tell you about, and that's our data transfer nodes. These are at, I'm sorry, I forgot the link here. These are at data.bridges2.psc.edu, and they support, oh no, it isn't there. And they support SCP, SFTP, rsync, and Globus Grid FTP for transferring data. Especially if you're transferring large amounts of data, please use the data transfer nodes. If you transfer a large amount of data through the login nodes, you can create a performance problem for other users. We have a lot of concurrent users that are trying to use the login nodes at the same time, so please be gentle on them. For data transfers, please use the data transfer nodes instead. Your data will end up in the same place. So the next subject is I want to go over just the command line details that you need to know for the rest of this presentation. When you connect to Bridges-2, you're going to get a command prompt. On Bridges-2, it will look like this. Prompts usually end in a $sign. For the sake of this presentation, I'm going to abbreviate all of my prompts to just the $sign, but when you're actually logged in, you'll see the full thing. The prompt will give you some useful information, such as the user that you're logged in under. My username is MWD. The system that you're connected to, Bridges-2, the specific node on that system. So we have, like as I said, a pool of login nodes. And generally, it doesn't matter which login node you're connected to, but if you run into an issue, you may need to give that information when you're submitting a help ticket. And this last part here, which is currently a tilde, represents your location, your current working directory. And a tilde means, a tilde is a shorthand for your home directory. So to actually run a command, you just type it at the prompt. So this would run the SSH command. The command that you're running is generally the first thing that you type after the prompt. And then the other thing that you need to know about is, and I'm going to use the terminology, arguments, parameters, options, flags. There is a formal distinction between these terms, but almost nobody knows what it is. So in our case, these terms mean pretty much the same thing. They are all the stuff that you type after a command, which will change the command's behavior. So for example, we might do SSH-P22, which tells it to use -port 22. And then I'll use -u MWD to say to log in as the user MWD. And then I will give bridges2.psc.edu as my final argument to say that's the server I want to connect to, or that's the system I want to connect to. So the other important thing to know for a command line is it's the topic of man pages. So whenever you connect to Bridges-2, you can search for manual documentation information. For example, I mentioned SCP can be used for transferring data. If you want to access the manual pages for SCP, the command is man. The -k argument will allow you to search all the man pages for anything that contains SCP. So for example, the output of this command will look like this. So you can see there are 1, 2, 3, 4, 5, 6 man pages that are related to SCP. And once you review these, you can see, okay, I don't know what these are. These don't look right, but SCP, there's a man page named SCP. That's the one I want to read. In order to read that man page, you can type man SCP, and that will bring up a manual page for SCP. This is an example of manual page for SSH. They are very long. I'm showing you the first 2 pagefuls, but it gives you all of the different options that you can use for that command and a description of what that command does and how all of the options behave. So this is one option to learn how to use a command instead of having to Google it. The next thing I want to discuss is, once you're connected to Bridges-2, how to actually prepare a molecular dynamics simulation. So the first thing that you're going to need is an initial configuration. That is going to be the same regardless of whether you're doing a GROMACS simulation or an AMBER simulation or a NAMD simulation or a LAMP simulation. It doesn't matter what simulation engine you're using. You always have to create your initial configuration files first. They will describe all the atoms and their initial positions. And there are a number of different tools you can use to generate them. I've listed a few here. CharmGUI is very popular. It's a web-based tool. VMD stands for Visual Molecular Dynamics. It's a visual tool. It's got a graphical user interface that allows you to visually and manipulate your molecules in 3D. And finally, some simulation engines come with tools as well. Like for example, GROMACS has its own suite of tools, but ultimately it doesn't matter what tools you use to generate your initial configuration. Just because you're using GROMACS does not mean you have to use its tools. Any system will do. And as I said, CharmGUI is going to be very, very popular amongst a lot of people. CharmGUI allows you to do things like create a simulation with a protein surrounded by water in a membrane, and it will assemble all of those pieces for you. The next step is to choose your force field. So I've listed here a handful of force fields that come with GROMACS. So I've listed AMBER, CHARM, GROMOS, OPLS. Those are shipped with GROMACS, but the force fields that come with GROMACS may not be the latest versions. So since each version of a force field will be updated over time as the researchers that develop it find more accurate parameters, you really want to use the latest version of your force field in order to get the most accurate simulation. So that means you may have to download and supply the force field yourself, even though we do bundle some with GROMACS. And then the final thing you need to think about is the physical properties of your simulation, what temperature you want to run the simulation at, what pressure you want to use it at, etc. And these typically don't go into your initial configuration files, but you will need them for the next step. The next step is using some engine-specific tools to process your initial configuration files. For GROMACS, most of your settings are written into an MDP file, which stands for Molecular Dynamics Parameters. This includes all of your physical settings, like I said, temperature and pressure. This is where you input those details. It also includes computational settings, such as how to write the output files, what names to use for the output files. You will typically run your simulation at a very, very short time step, like 2 femtoseconds between frames of your simulation, but you don't want to write out every 2 femtosecond frame. So it'll say how frequently to write out to your output files and lots of things along those lines. The distinguishing factor here between what I'm calling physical settings and computational settings is physical settings will affect your end result. They will affect the biology or chemistry that you're observing, while computational settings don't really change the output. They're just more kind of logistical aspects of things. So GROMACS has a special command that is used to process your input files. It's called GROMP. So the command is GMX GROMP. All of your GROMACS commands start with GMX. So it's GMX GROMP. And to get extra information about how this works, you can run man GMX GROMP to view the manual page for it. GROMP will read your initial configuration files, the force field you supply, and your MTP file and generate a TPR file for you. The TPR file from then on contains everything that GROMACS needs to run the simulation. So if you generate the TPR file in advance on your own resource, the TPR file is the only thing you have to copy to Bridges-2 in order to actually run your simulation. You don't have to copy any other data files. Once you're ready to actually start, what's the right way to say this? Executing your simulation, you should know that there are several phases that the simulation is going to go through. There are generally minimization phases, multiple equilibration phases, and then finally your production phases. Now, each phase is going to start with an MTP file that has special settings for that phase because these phases behave differently. So you have to put the different behaviors in the different MTP files, which means you have to gromp each MDP file and it will give you a new TPR file for each time. You use the output of one phase as part of your input files for the next phase. So the general procedure here is going to be you take your first MDP file, you gromp that to get a TPR file, and you run your minimization. Then you take your outputs from your minimization with a new MDP file, run gromp on that again, and now you'll get a new TPR file for your equilibration phases. So this loop of MDP file plus your output from your previous phase, send them through gromp, and then you'll get the new TPR file for your next phase. To actually run the phase, the command is GMX MDRun. We'll get into more details about this later. But as I said before, MDRun only reads the TPR files. As always, man GMX MDRun to get more information about that. One of the important things to know here is that nothing that I've discussed so far needs HPC resources. So you can do all of that at home on your home institution resources. You can even do that on a local laptop or something like that. Until you get to the production phase. Once you get to the production phase, that's the point where you're going to need to start running things on Bridges-2. Once you're in production phase, you don't need to run gromp in between stages anymore, because as you submit new jobs to continue your production phase, you're not changing any of the properties of the simulation. It uses the same properties of the simulation, so it can use the same TPR file. So let's talk about actually running these simulations on Bridges-2. I'm going to start with the CPU-based simulations because the GPU-based simulations build on top of this. There are all of your CPU-based simulations are going to run in the RM or RM shared partitions. In these partitions, every node has 128 CPU cores. So if you're doing an RM, then you have to, if you're doing an RM job, then you have to choose a multiple of 128 CPU cores. If you're doing an RM shared job, then you can choose up to 128 CPU cores. When you are setting up these jobs, there's a couple of important distinctions to make. There are two different types of parallelization that happen on CPU nodes. First is MPI gets used for communication between processes. And in this case, these separate processes are called ranks. There are two different kinds of MPI that you should be aware of for GROMACS. Whenever you are going to run a multiple node simulation, you're going to need to use an external MPI library, such as OpenMP. In this case, you will specify the number of tasks, the number of processes to spawn using MPI run -np, and then the number of processes you want to spawn. And that's the total number across all of your nodes. For a single node simulation, GROMACS uses the built-in thread MPI library instead. The reason why you do this instead of an external MPI library is because generally the thread MPI library is faster. So when you can use it, you want to, but it only works within a single node. In that case, you don't use MPI run at all. You just run GMX MD run, and you specify the number of processes to spawn using -ntMPI followed by the number. The other type of sorry, I'm getting ahead of myself. The important thing that you definitely have to be careful about here is the number of MPI ranks you use are going to be used to subdivide your system into basically different segments in three-dimensional space. In order to subdivide the system efficiently, you want to avoid large prime factors. If you imagine a big cube and you say, all right, I want to simulate this and I want to use 7 processes, the only way to divide a big cube into 7 equal spaces is to do 7 big slabs, which are not very efficient. You want things that are as close to cubic as possible. So instead, you should try to choose a number of MPI ranks that is highly composite. So -ntMPI 6 would probably perform better than -ntMPI 7 in this case. OpenMP is used for parallelization within each process. This is the other type of parallelization. Regardless of whether you're doing multiple nodes or single nodes, you can control the number of threads per process using the -ntomp option here. But in case, and of course, you definitely need to balance these, because if you were to, let's say we have 128 CPU cores and you want to use the entire node for your simulation, you could do 128 ranks with 1 thread each, or you could do 1 rank with 128 threads. Those will have very different performance characteristics, and neither one of those will be ideal. The ideal is usually around 6 to 8 threads per rank. So in this case, 128 divided by 8 is going to be 16. So you might want to try that -ntMPI 16 -ntomp 8, because that will allow you to use all of the cores on the node in a way that is probably mostly efficient. But you're going to need to tune that depending on your specific simulation. To add an extra bit of complexity, because the PME calculations are so different, you can select dedicated ranks specifically for PME. The PME ranks need different data for their operations. So by selecting a separate PME rank from all the other ranks, that means that the rest of your ranks don't need as much redundant data. They only need this, allowing you to have let's say you have 8 ranks and 7 of them, well, this would be a bad thing to do, but let's say 7 of them are used for your normal particle interactions and 1 of them is used for PME. It's a bad thing to do because I just said you want to avoid large prime numbers, but just for this example, we'll use this anyway. So you have 7 jobs or 7 tasks doing their particle interactions, 1 task doing the PME. That means that those 7 jobs doing particle will each take a different region of your simulation and will each only need to maintain the data and only need to keep track of the data within that one specific region, while the PME rank needs to track the data for the entire simulation. So you can see why the performance characteristics would be a little bit different there. because the performance characteristics are so different, you can dynamically choose the number of PME ranks and the number of OpenMP threads per PME rank. So each PME rank does not have to have the same number of threads as your particle-particle interactions do. To continue, it's very, very critical to benchmark your simulation with a variety of different combinations of number of PME ranks, number of MPI ranks, and number of OpenMP threads. I highly recommend using the Access Explore allocations for this. And just some extra notes, whenever you're doing this type of benchmarking or running on these types of nodes, all of the RM nodes charge by the core hour. I recommend running short benchmarks. There's no need to run benchmarks that are any longer than like 10 minutes. It just needs to settle in to a consistent pace, and then you can take a measurement. For optimal performance, I recommend you use these options, -pin on and -DLB on. -DLB stands for dynamic load balancing. It allows GROMACS to shift around some of the load and decide how big the different regions of your simulation should be to kind of make sure all the ranks have equal amounts of work. -pin on keeps your simulation from jumping between cores, and that's essentially just an operating system guideline to help the processor be more efficient. I don't have time to discuss the reasons why, but -NST-list tracks the number of particles around any given atom, which helps accelerate some of the other calculations. Setting different values for this can definitely affect your performance. I encourage you to experiment with different values of that. And then only for benchmarking, you should use -noconf out. That will prevent it from writing the final positions to your output. And -reset h-way or -reset step. What these do is, because in the very beginning of your simulation, it's going to be doing some dynamic load balancing and figuring out what the best way to optimize it is, you want to exclude the first part of your this benchmark from your timings. So reset h-way will say just take the second half, or you can use reset step to say, all right, only look at the last 10,000 steps. And then you can use -n steps to say run a simulation of exactly this length. So that way you're not trying to run like a 4-hour simulation when you're benchmarking. I want to show some quick batch scripts. So I'm going to skim over these options at the top here. This is all very well documented in the Bridges-2 user guide, which I linked earlier. I encourage everyone to set -E and -X, which will prevent you from wasting service units on failed runs. -E will cause things to stop, it will abort the execution as soon as there's an error. So to access the GROMACS software on Bridges-2, you want to use module load GROMACS. Then you want to use CD to navigate to the working directory with your simulation files in it. And then this is an example of what your GROMACS execution line is going to look like for a single node CPU script. So in this case, we're using 64 tasks. And if you do the calculations here, so we're saying NTMPI, so we're saying 18 ranks, but 4 of them are PME ranks. So that means that we're going to do 14 particle ranks and 4 PME ranks. Each particle rank gets 4 threads. Each PME rank gets 2 threads. If you multiply that out, 14 times 4 is 56, plus 4 times 2 is 8, adds up to the 64 cores that you requested. For multiple nodes, it's going to look a little bit different. You definitely set a larger number here. You want to load the GROMACS MPI module instead of GROMACS. That's the way you tell it that I want to use an external MPI library. And then you essentially, the rest of it is very similar, except you use MPI run -NP to specify the number of ranks you want to spawn. And then, as always, you want to use -NPME and -NTOMP and -NTOMP underscore PME to make sure you use all of the cores that you've allocated correctly. In this case, so this job has 128 cores per node, 4 nodes, so that's 512 cores total. For 3 hours, this job is going to use 1,536 service units. So that gives you an idea of how to do some of that mathematics. I'm going to try to go through this very quickly because I'm low on time. For GPU simulations, You get 40 cores per node, 8 GPUs per node. Service units get charged by the GPU hour. Retains all the same complexities, all the same options, all the same things that you need to tweak and pay attention to for CPU nodes. You have to do the same thing for your GPU nodes. Use these options to offload as much work to the GPU as possible. This basically tells GROMACS to do everything on the GPU because the GPUs are much, much faster than the CPUs are. When you set your number of MPI ranks, the thing that you need to know is that every MPI rank will get assigned one GPU, but each GPU can handle more than one rank. So you can assign multiple ranks to the same GPU. And then I highly encourage you to log in on a separate terminal and use NVIDIA SMI to check your GPU utilization while your jobs are running to see how well you're utilizing your GPUs. You can use an option like GPU tasks. In this case, it will basically say your first 3 MPI ranks should all be assigned to GPU 0, and your last 2 would be assigned to GPU 1. The thing to know here is, as I said before, PME requires a different amount of resources, so it's going to load a GPU in a different way. And then I'm not going to explain any of these. I'm just going to encourage you to set these environment variables, and this will be available in the documentation coming soon. The GPU batch scripts work basically the same way as the CPU batch scripts, except you have an extra line here to specify all those extra options to say run things on the GPUs. The multi-node GPU batch script you should almost never need because these GPUs are extremely fast, and you would need a very, very large simulation with millions of atoms in order to need to parallelize efficiently over multiple nodes. Almost any case when you're using GPU nodes, you're going to be fine sticking within one node. And to wrap things up, I want to tell you what's coming up soon. So the first thing is new modules. So I've been working extensively on preparing some new GROMACS modules. Right now, we have 3 modules in production on GROMACS, 2018, 2020.2 for CPU nodes, and 2020.4 for GPU nodes. But I have a number of modules that you should pay attention to in the pre-production. To view the pre-production modules, you can just do module show hidden avail GROMACS. It will list them all for you. And when you're loading a pre-production module, you have to do module load, and you have to specify GROMACS / the version number. That's the only way to get a pre-production module. If you just specify module load GROMACS, you'll get one of these instead. The pre-production modules have improved GPU offloading capabilities, improved CPU and GPU algorithms so they'll run more efficiently, and they're compiled against newer dependencies, which allows you to do a lot more things that you couldn't do as effectively before. The other thing I want to discuss is I've got new documentation that's going to be available soon. I was hoping to have it available before this presentation, but I don't have it quite ready yet. This is going to go through some specific procedures, what to benchmark, in what order, where to start. In general, I'll provide some basic numbers to start from and then guide you based on your results, whether you should try larger or smaller simulations from there. I will also provide example performance numbers for different sample systems. So there are lots of different kinds of simulations. For each kind of simulation, there are lots of different sizes that those simulations can be. And for each kind and size of simulation, I'll show the scaling behaviors on CPU nodes and GPU nodes. That way you can get an idea of just how, what kind of performance your simulation should get. To close, I want to say thank you very much for attending. Please feel free to email me at mwd@psc.edu. I'm happy to answer any questions about this presentation. For general help about using GROMACS or other tools on Bridges-2, I encourage you to reach out to help@psc.edu. That will get you into the official support system and make sure that me and other staff members make sure that all of us, we can take care of your request as quickly as possible. So thank you very much for your time. With that, I'll take as many questions as I can fit.
Yeah, no question in the chat, but I guess you've been holding back. But yeah, just unmute and ask Mitchell. Okay, here's, I don't know, Mitch, are you looking at the chat there?
Yes, I see. So okay. I'll read the question out for the benefit of people reviewing the recording. The question is it necessary to consider the geometry and volume of the simulated system when choosing NT-MPI, NT-OMP, for example, a rectangular versus a cubic simulation system? In theory, yes, exactly. In practice, no. The reason why I say this is because it's extraordinarily difficult to predict what the best distribution of NT-MPI and NT-OMP are going to be. So I highly, highly recommend trying a ton of combinations. With 10-minute benchmarks, they don't use up very many service units. So with an access explore allocation can give you essentially an infinite number of benchmarks as long as you run short ones. When I'm running benchmarks to determine what the optimal size for a production simulation will be, I will often end up running hundreds of different combinations of NT-MPI, NT-OMP, and different numbers of cores to make sure I'm choosing a total job size where this job will run efficiently. It's also important to test different values for NPME as well, different numbers of PME ranks. So, and even for the GPU nodes, test different combinations of assigning different tasks to GPUs. I mentioned earlier, I use 00011. The reason why I did that is for like a five task job being run on 2 GPUs. What that will do is that will assign the 4 particle-particle interaction tasks. It will assign 3 of them to one GPU and 1 of them to the second GPU, so that the PME can get more of a GPU because it usually needs it. Okay.
Do you see?
Yeah. Yes, I see.
Next question. Yeah.
I see. So the first question I see here is, we can study metal transition complex with GROMACS. I'm not sure. So GROMACS is mainly for Newtonian mechanics types of simulations for classical chemical interactions. Anything that's going to involve like a change in like the valence states or anything like that, I'm not sure if that's what you mean by metal transitions, but anything like that, GROMACS cannot do. So you can't have the transition state of a metal change over time. The next question I see here is, could you also provide any benchmarking data for some standard systems like STMV to compare the speed of GROMACS to other programs like NAMD and Amber? Yes, I intend to do exactly that. There are a handful of very commonly tested simulations, and STMV is pretty much the benchmark for around 1 million atoms. So I will be providing that, plus some custom ones to show larger and smaller systems. Absolutely. The next question. Thank you. Are we able to use our own compiled version of GROMACS on Bridges-2, or is it necessary to use the already installed versions from module load? You can run your own compiled version. However, I can tell you that compiling an optimized version of GROMACS for Bridges-2 is not a trivial task. There are a lot of compile time settings that you need to set just right, and there are a lot of dependencies that you need to make sure you load correctly. Whether you want to compile and prepare all of those dependencies on your own as well, you can do that. If I recall correctly, there are about 9 different software packages that GROMACS depends on. Or if you want to run your own version of GROMACS with some maybe custom patch, then you can use the same version of the dependencies that we already provide, but just compile GROMACS against our dependencies. That would be fine too. I recommend, unless you really need to, I recommend using the GROMACS modules that we provide though. It'll save you a lot of time. And then we have a clarification. So metal transition complex as a ligand. I'm afraid I still don't quite understand what you mean. I will be honest and say that my personal background here does not involve a lot of protein simulation. I tended to simulate mostly empty bilayers so that I could observe lipid dynamics within those bilayers. When it comes to protein ligand interactions, I don't have a lot of experience there. But if you send me an email, I can look into this and give you a more educated answer once I have a chance to research it a little bit. I'm trying to go through as many questions as I can as quickly as I can. I've got a couple minutes left. Any others? Sure thing. Is it possible to submit a simulated annealing job to production runs on Bridges-2? In the guidelines, it is mentioned that it has to be a constant ensemble, so I wasn't sure if we were able to run something where the target temperatures, pressures change. Yes, you absolutely can. That is so there are a variety of different types of more complex jobs that you can absolutely set up. In this, as you saw, it was very difficult to get through the materials I presented in the time allotted. So I didn't have to have chance to discuss things like simulated annealing and replica exchange and umbrella sampling. There are a lot of advanced techniques that GROMACS can absolutely handle. They are supported on Bridges-2, absolutely, but they are more complex. If you reach out to me at mwd@psc.edu or better yet, through help@psc.edu, I would be happy to assist you with setting up those types of jobs as well. All right, by my clock, I've got 1 minute and 15 seconds for final questions. Sure thing. One thing that Zoom doesn't have, unfortunately, is doesn't have any way for me to know if anybody's typing. So somebody could be typing a question right now, and I wouldn't have any way to tell. But I'll definitely give you the full time. Type fast.
Thanks, Mitchell. Looks like that's probably all for the questions. Oh, here's the late submission.
Sure thing. Summarize the node counts for each of the partitions. Yes, absolutely. So the RM partition has 488 nodes in it. And all of those nodes are identical. The RM shared borrows from the same partition or from the same pool of nodes as the RM partition does. As far as the GPU and GPU shared partitions, that partition is much smaller. We have 34 GPU nodes, and 2 of them are reserved for smaller jobs. So the GPU and GPU shared partitions have access to only 32 nodes. I definitely encourage you guys, especially if you are running smaller simulations and smaller benchmarks, submit your jobs to the shared partitions. You will almost certainly, they will almost certainly be allocated more quickly. So yes, 488 nodes for the RM and 34 nodes for the GPU partitions. Okay, and I think with that, we're out of time.
Thank you, Mitchell. Thanks for everyone for joining today. We appreciate Mitchell's for being here. And as I mentioned earlier, it has been recorded and will be posted on the web sometime next week. If you have any questions that linger beyond this time, please send to help@psc.edu, and either Mitchell or I will get back to you as quickly as possible. Thank you for joining once again, and enjoy the rest of your day.